Welcome everyone. So glad you're joining me for this explainer. Today, we're diving into the massive, awe-inspiring, and frankly, highly complex world of industrial plant construction. If you've ever driven past a huge refinery or chemical plant, you've probably marveled at the sheer scale of the equipment towering up into the sky. But have you ever stopped to wonder how human beings actually interact with those giants? Well, today, we're going to unpack exactly that. We're going to look at the engineering and construction magic that lets humans conquer these towering steel beasts safely and efficiently.
Okay, let's dive into this. Have you ever really looked at the size of the equipment in these facilities? We're talking about pressure vessels and chemical towers that can easily hit 100 meters tall. That is the size of a 30-story skyscraper. And these aren't just giant hollow tubes, they are highly complex machines that need constant human monitoring, maintenance, and operation. But obviously, humans don't have wings. So how on earth do operators and mechanics safely reach the top of a 100-meter-tall, boiling-hot, pressurized steel cylinder to do their jobs? To figure out how it's done, we've got a great roadmap today. We'll cover platform and ladder basics, why they're necessary, the ground assembly method, handling real-world interferences, and finally, mega towers and dress-up. Let's get to it.
Section 1. Platform and ladder basics. Let's define the components.
When you look closely at a vertical vessel, you'll notice it's completely surrounded by steel structures. Now, these aren't just random additions, right? They're carefully engineered access points. Globally, when we talk about making these plants accessible, we use three key English terms: the platform, the ladder, and the handrail.
Let's break those down formally. The platform, that's your flat, usually graded steel surface where the operators actually stand to do their work. The ladder is exactly what it sounds like. The vertical access route letting workers climb up from the ground or move between different platform levels. And the handrail is absolutely crucial. It's the safety barrier around the platform that prevents a potentially fatal fall. Put them all together, and it's basically a safe, navigable highway system wrapped right around the equipment.
Moving on to Section 2. Why are they necessary? Let's look at the purpose behind these structures.
You see, a pressure vessel isn't just a set-it-and-forget-it kind of machine. Operators need actual physical access for some pretty critical tasks. I mean, they need a stable place to stand, to turn heavy manual valves, or to get up close to read pressure and temperature gauges. Plus, instruments on the upper levels constantly need recalibration or repair. Oh, and every so often, workers have to open massive manholes to physically crawl inside for cleaning and inspection. And here's a huge safety point. Climbing a straight vertical ladder for dozens of meters, it's completely exhausting. So the platforms act as mandatory rest stops. Without them, workers would risk extreme fatigue, which is just incredibly dangerous when you're that high up.
Section 3. The ground assembly method. A much safer approach.
Let's compare how you actually build these things. Assembling everything up in the air might sound intuitive at first, but imagine the reality of that. A worker has to go up in a man lift while a massive crane holds a heavy piece of steel platform. Then they have to align and tighten hundreds of bolts and nuts while literally dangling dozens of meters in the sky. Doing that piece by piece, handrail by handrail, it's agonizingly slow. It ties up incredibly expensive cranes and man lifts, which makes costs just skyrocket. But most importantly, high-altitude work is just inherently dangerous. So the industry standard is actually ground pre-assembly. It's safer, it's cheaper, and it's vastly more efficient.
Think about it like this. Workers lay the platform grading right there on the dirt. They can attach the handrails and tighten all the bolts and nuts on solid ground. Once that entire segment is totally secure, a crane just lifts the whole unit up at once. It's a brilliant way to minimize risk and really maximize productivity.
Section 4. Handling real-world interferences. This is where design meets reality.
Now, if you compare a pristine, mathematically perfect engineering drawing to the reality of a real plant, well, you see a major challenge. A construction site is like a dense jungle of pipes, structural steel, and electrical cable trays. During the design phase, it's honestly nearly impossible for engineers to perfectly predict the exact routing of every single tiny pipe and cable. So what happens? When that pre-assembled platform is lifted into place, it frequently bumps right into a pipe that simply wasn't on the original 3D model. In the industry, we call this an interference or a clash.
So how do we solve a clash? Workers have to improvise, safely of course. First, they find the exact point of the clash. Then they quite literally cut a section out of that brand new pre-supplied platform right there on site so the pipe can pass through. But as you can guess, cutting a steel platform weakens it. So step 3 is absolutely critical. They have to engineer, fabricate, and weld new support structures on the fly to make sure the platform can still safely hold the weight of the operators.
Actually, fixing these interferences, the cutting, modifying, and re-welding of platforms, is one of the most common and time-consuming reworks on any planned construction site. But eventually, all the clashes get resolved, all the bolts get tightened, and you get an incredible result. A fully completed vertical vessel, heavily armored with platforms and ladders, totally ready for safe operation.
Section 5. Mega towers and dress-up. Scaling things up to 1,000 tons. Now, in massive oil and gas projects, you'll run into cylindrical towers that are 10 meters in diameter, over 100 meters tall, and weigh upwards of 1,000 tons. At that massive scale, the standard installation methods we just talked about completely fall apart. I mean, building scaffolding 100 meters into the air requires a huge amount of material, and it's absurdly expensive. On top of that, trying to use cranes to lift platform segments that high is agonizingly slow and super dangerous because of high-altitude winds. Literally, every minute a worker spends 100 meters in the air, productivity plummets and the safety risks skyrocket.
So here's the crucial point. We have to rethink the orientation of the work entirely. And that brings us to a really fascinating industry technique known as dress-up. Think about it. If it's too dangerous to build the platforms while the tower is standing up, why not build them while the tower is laying down? These massive columns are actually delivered to the site and laid completely horizontally on the dirt.
While that giant tower is resting safely on the ground, workers surround it with low-level, cheap scaffolding. From there, they can easily and safely weld all the platform supports, attach the ladders, bolt on the handrails, and even wrap the entire vessel in thermal insulation. Basically, the vessel is being fully dressed for its final job, all while sitting just a few feet off the ground. The productivity is absolutely incredible, and the safety risks are kept to an absolute bare minimum.
By dressing the tower on the ground, engineers totally bypass the dangers of extreme heights. But this brilliant solution creates a whole new, massive problem. You now have a 100-meter-long, 1,000-ton steel behemoth covered in delicate platforms and insulation just lying on its side. So how in the world do you safely lift a fully dressed, skyscraper-sized object upright without crushing those platforms or dropping the tower? Well, that takes some of the most spectacular heavy lifting cranes on the planet. But that is a fascinating story for another explainer. Thanks so much for joining me today, and keep questioning how the massive world around you is built.